that we find important is trying to understand the genetic makeup of our seagrass. So like Nick talked about, we can do intentional restoration. So if we know that this grass was from a certain area that has a lot of heat stress, then it might be more resilient to heat, and so we can intentionally plant that in other areas. And so that's great. The next step then would be to breed different organisms together, same species, right, but make new hybrids. And so you can't do that unless you understand how the organisms reproduce. And so understanding flowering phenology, or the timeline over which the plants reproduces is really helpful. And so that is what Mallory has been focused on this summer.
Thank you, Krista. So, good morning, everyone. My name is Mallory, and today I'll be talking about my summer internship project, evaluating the effects of Florigen on flower production and flower phenology in Thalassia, Testudinum. I made this quicker. Seagrass ecosystems provide a variety of important ecosystem services, including habitat and nursery, ground for a variety of organisms, a food source for grazers like manatees and green sea turtles, and long-term carbon storage in their sediments and root systems. However, seagrasses face numerous stressors, including increased turbidity, algal blooms, damage by boats and anchors, and destructive fishing practices. And these stressors can reduce water quality directly or damage the rhizome network of seagrasses, threatening their health and persistence. And there are several factors that can increase resilience within seagrass ecosystems, but here I'll focus on those specifically within seagrass meadows. And there are several factors that can increase resilience in seagrass meadows, including species diversity, energy reserves, continuous habitat, and seed banks. And this project focuses on another important factor, genetic diversity, which can increase the likelihood that some individuals in a population will be able to tolerate those environmental stressors. Seagrasses reproduce in two different ways, primarily by asexual reproduction or clonal growth, where horizontal rhizomes, shown in that picture on your left, produce genetically identical shoots that allow the meadow to expand. But they're also capable of sexual reproduction, where they produce flowers and seeds. And unlike clonal growth, sexual reproduction increases genetic diversity in the meadow because it creates new genetic combinations. And as I mentioned before, genetic diversity is one of those ways that resilience can be increased in seagrass meadow. And for this project, I focused specifically on Thalassia testudinum, or turtle grass. And unlike many better studied seagrass species, turtle grass is dioecious, meaning that male and female flowers are found on separate reproductive shoots. Oops, sorry, I'm getting spoilers now. Male flowers produce pollen, and female flowers, of course, receive that pollen and can develop, now stem, into a seed. Male flowers for turtle grass remain in bloom for about 24 hours, compared to about 3 days for female flowers. And currently the only way that we can determine the sex of a turtle grass shoot is observing it flowering. Another difference between the two, male shoots can produce up to 3 flowers per season, while females produce only 1. But there are several challenges to studying seagrass flowering. The first being the mechanisms controlling the transition from vegetative growth to sexual reproduction are not well understood. Stress is thought to play a role in this process, but we're not sure of the exact threshold that triggers flowering. The second challenge would be that flowering is relatively uncommon in seagrasses, since primarily they're going to reproduce asexually. Third, flowering is seasonal, and for turtle grass, it occurs from March through May, which gives us a limited window to study reproduction. And finally, we don't know if wild populations have sex ratios that are even conducive to successful reproduction, since, as I mentioned, the only way to determine sex is to observe flowering directly. And flowering is controlled by a complex network of hormones and regulatory pathways, which as you can see in this figure, but here we're only going to focus on just one, Florigen. And Florigen is a plant hormone that's commonly used to induce and promote flowering in terrestrial plants. But for this project, we focused on, could Florigen be a potential way to induce flowering in photographs? So if we could eventually induce flowering outside the normal season, we could expand our window for studying reproduction and potentially manipulate flowering timing. And flowering of both male and female flowers has been previously observed in the West Nursery, but we never observed any successful pollination. So if Florigen could help manipulate flowering timing, it could potentially bring those male and female flowers into better synchrony and maybe see some pollination. So this led to 3 research questions. Can Florigen induce flowering in turtle grass? Does Florigen affect the timing and bloom period of male and female flowers? And does Florigen increase synchronization between male and female flowers? To address these questions, I focus on 3 objectives. One being determine whether Florigen increases the number of reproductive shoots or flowers. The second being determine whether adding Florigen affected the duration or timing of blooming. And finally, determine whether Florigen increases synchronization of male and female flowers. And the study, of course, took place right here in the Seagrass Nursery in our 6 photograph tanks. And the 6 tanks were divided into 2 treatments, Florigen and non-Florigen. Florigen was added to tanks 10, 12, and 15, while tanks 11, 13, and 14 served as our non-Florigen controls. And Florigen was applied within 1 to 2 days of the start of blooming in the nursery. And to apply the treatment, the water level in the tanks was temporarily lowered so that we could maintain Florigen at the recommended concentration in the 3 treated tanks. And the tanks were then covered during treatment, and once treatment was complete, they were uncovered and then refilled back to their normal state. Flowering was observed for 1 month, and when a new reproductive shoot was observed, it was tagged with one of these tags here, so that we could continue to observe that flower and monitor it over the course of the observation period through photos. And the photos were taken at the same angle for each observation, so that we could observe individual flowers, and for males, multiple flowers on the same shoot. And during the observation period, for each observation, we would take the tank number, shoot ID, flower number, sex when known because we didn't always know depending on the phase of the flower, the flowering phase, and then a photo number to keep track. And in the data set, I distinguished between reproductive shoots and flowers. A reproductive shoot was counted if any signs at all of flowering were observed during the observation period, and individual flowers were tracked separately since, as I mentioned, males can produce up to 3 flowers per shoot. And for identification of flowering phases, I used this guide from a previous study, and for males, I focused on 3 key phases: A, the budding phase; B, the bloom phase; and G, the post-bloom phase. For females, there's only 3 documented phases. However, since, as I mentioned, there was no successful pollination observed in the study, which would be that image J on the bottom there, I added a new phase, J1, to track females that finished flowering but didn't produce a fruit. And photos were initially taken daily and then every few days during the observation period. And I used these photos to keep track identify the sex and phases of flowers over time afterwards. And the first objective was to determine whether Florigen increased the number of reproductive shoots or flowers. And this first plot shows the number of reproductive shoots by sex and treatment. And we have females on your left, and then males on the right, with number of reproductive shoots on the y-axis. And then Florigen treatment is shown in green and non-Florigen in yellow. And for females, there were slightly more reproductive shoots in the Florigen treatment, while for males, the number of reproductive shoots was relatively similar between treatments. And this next plot shows the number of flowers produced. And since as I mentioned earlier, females produce only 1 flower per shoot, so the number of flowers produced was the same as the number of reproductive shoots. And for males, Interestingly, non-Florigen males produce more flowers per shoot than the Florigen males. So that was an unexpected finding here. And then the second objective, to determine whether Florigen affect the duration or timing of blooming. This plot shows the number of days each individual flower was in bloom by treatment and sex. Interestingly, males consistently remained in bloom for 1 day, but females showed greater variation. And Florigen increased the variation in female bloom duration, including that 4-day outlier right there. However, the mean bloom duration, which is marked by the X's on this plot, was slightly higher in the non-Florigen treatment at 2.5 days compared with 2 days in the Florigen treatment. And this plot is where we're getting a bit more complicated, so I make sure to carefully visualize this. So this is the cumulative number of reproductive shoots over time by treatment and sex. And for females, we can see that the number of reproductive shoots reached a plateau or in the middle of the observation period, but the females both followed the same kind of shape or trend over time. And for males, we can see that the non-Florigen reproductive shoots began appearing a bit earlier, but both treatments continued to increase for males after that initial plateau in the middle of the observation period. And then this plot shows the cumulative number of flowers produced over time. And again, since females produce only 1 flower per shoot, we see the same curves here that we see in the reproductive shoot. And then, interestingly, for males, non-Florigen began to flower earlier and increase more rapidly than the Florigen males. And we can see that steep curve towards the end of the observation period. And our third objective, to determine whether Florigen increased synchronization between male and female flowers. These plots show the number of male and female flowers in bloom each day for the observation period, with the Florigen treatment on the left and the non-Florigen on the right. And for Florigen treated tanks, we see 3 days of overlap between male and female flowers in bloom, and these primarily occurred in late April. In comparison, for the non-Florigen tanks, we see 5 days of overlap, and these occurred a little bit earlier, primarily in late March. Florigen may have affected male and female flowers differently. It potentially increased flowering in female shoots. However, we saw more flowers per shoot in the non-Florigen treatment than in the Florigen treatment. Florigen did not appear to change when reproductive structures or flowers began appearing, but it did increase the variation in female bloom duration. And finally, Florigen did not increase the synchronization between male and female flowers, which we can see based on less days of overlap in that previous plot with the Florigen treatment. However, these results only reflect one specific time, treatment period, and dose of Florigen. So we can't just say that Florigen definitely didn't work. We can keep trying other things and mass variables, things like that. So Florigen did not produce the expected improvements in flower production and synchronization for this trial. However, the results do provide useful information for designing future experiments. For example, future trials could test other hormones or combinations of hormones. And because we now have reproductive shoots of known sex, future experiments can control the sex ratios within the tanks and investigate the basis of genetic sex determination in turtle grass, which I find really exciting. And then the updated flower and bee strategy will improve identification of female flowering and pollination outcomes, as well as help account for some of the phases that might have been missed depending on observation timing. I'd like to thank everyone who contributed to making this project possible, especially my mentors and the FLS research team. And I'd also like to give a special thank you to Margot Cleary and Alec Brockman for making this internship possible. And thank you all for listening, and I'm happy to take any questions you guys have.